Okay, so today we'll be talking about the IDEA, IPEBB, Innovative Design Automation Framework for Integrated Power Electronics Building Blocks under the URI Power Electronics Lab. And yeah, so continue. So our ultimately our technical directors are Professor Yonho Chiang and a PhD candidate Shushan Zhang. And yeah, so our team is broken up into two groups, hardware and software. I am Gianni, and I'm on the software team with Justin. He's a computer engineering and applied mathematics major, and I'm electrical engineering and German. And on the hardware team, we have Max Bongiovanni and Patrick Felice, who are both electrical engineers. And yeah, so just a quick overview of the company. So there's three current projects being worked on. There's the real-time simulator in educational laboratories for advanced electric transportation technologies, as well as the novel power conversion system and power management control for water monitoring stations, and our design project, which is under the hardware accelerated machine learning EDA, and for power electronics, that would be under the IPEBB. Yes. Um, and yeah, so our project motivation, so ultimately, our goal is to design an efficient power conversion system that can be used in a modular fashion. So ultimately, the problem is that there's a labor-intensive circuit design process, which in general it takes a while to design a circuit, as well as using SPICE simulations. These take a lot of time, and in the end, they ultimately don't yield the optimal results that are needed for a design. And yeah, so our proposed solution is a machine learning based design method in conjunction with the standardization of power electronics. So it's ultimately a SPICE-based simulation, which it's proved in the past to reduce the time by speeding up to about 60 times compared to various other circuit simulations such as PowerSim and LT-SPICE. Yes. So, yeah, and so our anticipated best outcome, as you can see in Figure 1, that would be we would have two different drones. One would contain two IPEBB power conversion systems, and the other one is the 6S that would include four. And we would ultimately use the reinforcement learning based power electronics design tool to optimize and choose the best component values for the power conversion system. And yeah, so ultimately, so the goal is to optimize the reinforcement learning based power electronic design automation framework, ultimately enhancing the accuracy and speed. And then upon optimizing, we can then extract the design parameters from the power electronics design automation tool, and then implement them and evaluate multiple IPEBB boards on both PCS1 and PCS2. And finally, we plan on applying the completed boards to two different drones and note any changes in the performances. And just some key technical accomplishments towards achieving the ABO. So we've had the drone assembly, which you can see on the right-hand side. This is just how a simple quadcopter or drone looks with the whole layout with flight controller battery, various other accessories, and then the motor drivers and then the motors. So that's the overall concept of a drone. Then as well, we have the circuit topology, which our hardware team decided upon an LOC, half-bridge LOC resonant converter. Um, and then on the end of the software, so we had the power electronics design automation framework. This was ultimately given. So we have our goal was to figure out how to operate it, how to ultimately how to change parameters, set the inputs and outputs of the circuit, and yeah. And yeah, so some of the economic impact for the company. So as we know, so the URI Power Electronics Lab is a research lab, not a company. Although through commercialization and patent, we can receive patents and licenses. And the industry efficiency, this can be improved through productivity. And furthermore, if we're able to bring this product to market, it would decrease costs overall for circuit simulation. And yes, so continuing on, um, yeah. So here's just a simple overview of what our project looks like. And yeah, so I'm just going to begin with my technical contributions. So the main thing that I focused on was the M&A calculations, otherwise known as the spice-based um, modified nodal analysis. This is something that was ultimately and everyone's learned this in ELE 212. So ultimately, it's like KCL, KVL, and all of the various circuit design and circuit analysis tools. And yeah, so you can see on the right-hand side, we have our circuit, the LOC half-bridge resonant converter. And this is what the circuit would look like from the perspective of doing the M&A calculations. So it ultimately sets each component as a resistor value, and we run like various nodal analysis and KVL, KCL conventions on each of them, trying to figure out the best component value, and yeah, running through numerous iterations until we get to the right component. And yeah, so furthermore, I wanted to mention, so the total number of matrices is equal to the time step multiplied by the iterations per time step. So this would end up ended up being like 10,000 matrices being performed in one simulation, which would take quite a long time. So therefore, this is the proposed method. Yeah, and so here's just a block diagram of what it would look like. So we have various calculations, and they're separated into groups, such as the diode controller. So that's mainly for like diodes and other. If it's a synchronous diode, then that's just MOSFET. So it would be under like the switches. But yeah, so there's various other. So there's one for switches, one for reactive components, and one for sources. And so it ultimately goes through systolic arrays, which take the values, sum them, and ultimately output the best component values for each of the components. And yeah, so I was able to assist. Furthermore, I was able to assist with the hardware team in the design from simulation to prototype production. And yeah, so uh, now I'm going to just mention a little bit more. So this is what the circuit simulation looks like. It looks very similar to LT Spice, just a bit faster. And yeah, so you can see the goal of this whole project is to derive the net list which will give the best component values for the optimum efficiency, the optimum output, and so forth. And this is ultimately what it will look like in our code. So this is very common in spice-based simulations. And now I'm just going to pass it off to my group member after this. So yeah, and so some of my technical accomplishments before April 15th, that would include running the code given our desired input and output parameters for the PCS, as well as doing a comparison between hardware teams' calculated values versus our simulated values. And furthermore, we plan on implementing the design framework to the Amazon web-based services to be public access, and then I end up extracting the design parameters. And furthermore, I plan on assisting with the hardware team with any of the PCS development, and finally optimizing the power electronics design automation framework to enhance the accuracy and speed. And now I'm going to pass it on to Justin.
Hi, my name's Justin, and I was part of the software team with Gianni this semester. My primary technical contributions included studying and testing the RL-based power electronics design automation tool. This involved a lot of studying machine learning and trying to learn Python. I was also responsible for assisting the hardware team in building the drones, as well as our first half-bridge LLC resonant converter. So today I want to talk a bit about machine learning and how we're using it in our project. So there are three types of machine learning: supervised, unsupervised, and reinforcement. We are using reinforcement learning in our project. The advantages of reinforcement learning include that it's useful for situations where you don't know the outcome. For example, in the other two types of machine learning, supervised and unsupervised, you train the model using a data set. If you notice, in reinforcement learning, we train it by having it interact with an environment. This is because we don't have a data set to train the model with. We don't really know the predetermined outcome. We don't know what it should be. We want the machine to figure that out for us, which is why we chose reinforcement learning. The key disadvantage of reinforcement learning is that it's computationally expensive and time consuming. We're able to circumvent this by using a FPGA instead of running it using software. It's still computationally expensive, but it speeds up the agent dramatically. Reinforcement learning involves an agent and an environment. The agent will make an action, the environment will see that action, calculate a reward, and give that back to the agent. The agent, using proximal policy optimization, PPO, will try to maximize the reward it gets. Therefore, it'll keep making actions in its best interest to maximize its reward. In our project, the environment is a half-bridge LLC resident converter. So our application of reinforcement learning, to start, we give the agent our design constraints. This includes an input voltage, our output voltage, and our output power. This is what we want to see come out of our converter. The agent will take these constraints and it will make an action. This action includes either decreasing a capacitor or inductor, which is shown numerically by a -1, increasing the inductor or capacitor, shown numerically by a +1, or not changing one of the values, numerically shown by a 0. If the inductor or capacitor were to decrease in value, it is shown as a negative point, uh, -0.02, or a decrease of 0.02. And if it were to increase one of these values, it's preset to be an increase of 0.04. Next, the environment will go over those modified nodal analysis calculations that Gianni just described, so I will skip this part. Next, the environment will calculate its reward and send that back to the agent. The reward is based off of how close the agent got to our target voltage, our target output voltage that we want the converter to give us, and the agent's efficiency, which is simply power out over power in. Finally, one of those entire loops from agent to action to environment to reward back to the agent, that whole loop is called an episode. There are a couple ways to end an episode. One is if the agent has run over 200 times. The agent is allowed to take multiple actions. Actually, it's supposed to take multiple actions before the environment calculates and sends a reward back. The agent is allowed to take up to 200 actions, and then we will end the episode. Another way for it to end is if the agent picks an invalid parameter. An invalid parameter for one of the inductors or capacitors would be if one of them drops below 0. Obviously, you can't have an inductor or capacitor that is below 0. Or if the inductor or capacitor value increases over 1, we will also end the episode. Finally, we'll end the episode if the agent achieves great efficiency. This means that the agent has made at least 100 actions and it's at its maximum efficiency, or the highest efficiency it's ever been at. Obviously, if we were to end it at action 1 or 2, it would be at its highest efficiency ever, which is why we wait for it to reach at least 100 actions to see if it's at its highest efficiency. Then we'll end the episode and begin the loop again. My technical accomplishments for next semester include finishing building the drones, optimizing the power electronics design automation tool we just talked about to enhance its accuracy and speed. We'll then run the tool on a FPGA cloud service, most likely going to be AWS. We will extract design parameters from it, get our answers from the agent, and finally we will build an integrated power electronics building block, one of the iPEBBs that our project is based off of, and we'll finally install that on a drone to see if it works. Next, Max will introduce what the hardware team has been working on.
Hello, my name is Max Bongiovanni, and from here on we will be talking about the process of developing the hardware for the integrated power electronics building block. My technical contribution to date has been to research the drone technology that our iPEBB will be providing power to establish the parameters of which we will be basing the power conversion system off of, and to run the simulations of the circuit. To begin the development of the hardware, we focused on the hexacopter. The source of the power for the hexacopter will be coming from the HRB 6-cell lithium polymer battery. This provides 5,000 mAh and 22.2 volts. The load for the hexacopter will be 6 DJI E800 motors, all of which require up to 54 amps of current together. After we had established the source and load, we decided to use half-bridge LLC resonant converters as the basis for our iPEBBs. Using the parameters of the source and the load, we calculated all of the component values for the converter and then went to verify the results with simulation. In order to simulate the LLC resonant converter, we used the software Plex. And to control the switching frequency, we used an open-loop control system. Our aim was to have around 100 kilohertz for the switching frequency. After the output of the simulation verified the component values of our calculations, we went on to build a physical prototype of the converter. Some of my remaining challenges for the future include finishing the physical prototype of the LLC resonant converter, developing a closed-loop control system, turning the converter into a PCB with the new control system, and making a configuration method where multiple of these iPEBB PCBs will be able to work together in series or in parallel.
Hello, my name is Patrick Feliz, and I was part of the hardware team with Max von Giovanni. As far as my technical accomplishments, I researched LLC resonant converters, which is seen in Figure 5. I've also did calculations for the component values of this main PCS, which I'll talk about the component values a bit later, as well as design the physical prototype of the LLC resonant converter. So the LLC resonant converter consists of 5 main parts. First being the inverter, second part being the resonant tank, the third part, the transformer, the fourth part, the rectifier, and the fifth and final part, the output filter. Out of all the resonant converters on the market, LLC is the most commonly used. This is due no, to several different things, but I'll kind of compare the LLC resonant tank networks in a bit more slides later down the line. But we can see the unique feature is its voltage gain. As we can see in Figure 6, we have this voltage gain graph representing the LLC resonant converter, and when you can see normalized frequency is just the frequency of the resonant tank over the switching frequency. And if they're equal, we can obtain a unity gain of 1. And if we decrease the switching frequency of the MOSFETs, we can actually achieve a higher voltage gain, which is represented in the inductive region. And if we increase the switching frequency greater than the resonant frequency, then we can experience a buck operation. So we will actually have a lower voltage gain, less than 1. In practical settings, we try to steer away from the so-called the capacitive region, which is shown in the graph and highlighted in red, because we can see that the voltage gain drops rapidly, if we alter the MOSFET switches, this sudden decrease in voltage gain, you can see that the slope is really, if we change from 0.4 to 0.3 normalized frequency, we can see that the voltage drop or the voltage gain drops significantly. This can actually damage our components and even blow up. So this is something we actually do not want to happen, once we're designing a circuit, right? We don't want the drone to blow up while in altitude, right? That's never good. So we try to stay in this inductive region in the blue. As for the inverter design, there's 2 different possibilities you can use, either a full bridge or a half bridge configuration. Half bridge just meaning that there's 2 MOSFET switches. At the inverter stage, the MOSFETs turn on and turn off at different stages. As you can see in figure 7, we just did a quick demo of the inverter stage, and we can see the blue would represent 1 MOSFET turning on and the red would represent 1 MOSFET being shut off. So this altercation of on and off switching is what can be used for our LLC resonant converter. As you can see in figure 8, we actually did a setup in the lab consistent of an Arduino Uno, which supplied PWM signals of 50% duty cycle and some dead time between the signals on and off stages, as you can see again in figure 7. And then the input voltage is what we applied, or that's being used as a battery. And we can see in figure 9 the resulting input battery and the resulting result due to the inverter. Since we're operating less than 1 kilowatt for the drones, we can stick fine, or we're fine with sticking with the half bridge instead of the full bridge. As far as the tank value, as far as the tank design, there's different types of networks we can use. As you can see in figures from 10 to 12, there's LCC, which consists of 2 capacitors and 1 inductor. LLC, which we're currently using for our project, which consists of 2 inductors and 1 capacitor, or a series resonant network, which just consists of 1 inductor and 1 capacitor. I mean, obviously, different applications have its benefits in withdrawals. As far as our case, we chose the LLC resonant converter due to its high or its low switching losses in the MOSFETs, as well as we can achieve a higher voltage gain compared to, let's say, the SRC network. And the efficiency is actually higher than both the LCC and the SRC. So that's what we really want to achieve, a really high efficiency for our application. And although the complexity is a bit more complicated than the SRC, yet the efficiency, what we care about in this case, exceeds both networks. As far as the transformer, rectifier, and the output filter is simply just a capacitive filter, nothing special about that. And as for the transformer, we weren't able to actually implement the transformer during this semester, but definitely during next semester, we're definitely going to implement it. The transformer is just used to isolate both circuits, so these circuits aren't electrically connected. They're they have different grounds, so they're actually two completely different circuits. We're just combining them using a transformer for safety purposes. So this is transformers are typically seen in your chargers, to protect yourself actually from the voltage that's coming out of the outlets. And in our case, we're using center tap rectifier, but since we weren't able to implement that, we're just using a full wave rectifier for an open loop testing. As far as my technical accomplishments for the next semester, I definitely want to get finish building the physical prototype of the PCS, then running verification tests, to ensure everything functions uh, as predicted. And then once we get the actual physical prototype to work, we can then move on to maybe designing a PCB for this prototype so that we don't have to use a bunch of wires and a bunch of different boards just to achieve this PCS. And then after designing the PCB, next step would be to implement this into both drones and get the drones flying. As for key technical accomplishments towards achieving our ABO, which include the M and A calculations, running the Peter tool using our desired input and output parameters for the PCS, doing a comparison between the hardware teams and the software team's calculated values to see which yields a better result, building a physical prototype of the PCS for verification, designing the iPEBB board of the PCS that would be used for the drones, and then determine any improvement in the drone's performance that need to be altered. Again, we just want to reiterate our thank you to our two technical directors, Professor Jiang and Shushen Zhang. Their extensive support and guidance has been extremely beneficial for our continuation in this project. As well as we want to thank our program manager, our program or capstone director, Professor Sunak, for making this opportunity possible for us, to create such a meaningful product for Professor Jiang and Shusheng. Thank you for your time. Thank you.